And then, yeah, I will give the word to you, Tiago. Thanks.
Thank you very much, Cyril, for the invitation. Let me just mute something here. I cannot, just 1 second, sorry. Um, I have joined it as well on my cell phone because I want to make sure that I see the chat, but it's giving me, okay. It's giving me back. No, I fixed it. Okay, so thank you very much for the invitation. One thing, if people have questions, please feel free to stop me. I cannot see the chat very well here, so please, if you have a question in the meantime, make yourself known. Please, Cyril, let me know if there are interruptions that I should be aware of. Indeed, this talk is about this preprint we put out recently um, about graphs and hypergraphs. It's joint work. We did it with Lito, Tilo, and Manlio. You can get the paper there, and it's I did quite a bit of advertising on social media, so you should probably know where to find it. So indeed, what we want to address here in this talk are this certain set of premises that underlie a lot of the recent literature on so-called higher order networks, which I'm assuming a lot of you are familiar with, right? So there has been this increase of papers in the last maybe 5 or a bit longer, 5 years at least, 5, 6 years of papers modeling, using hypergraphs to model interacting systems. And a lot of these works are based on the following set of claims, right? So what maybe the most basic assumption here that is taken is that graphs, which have been used for network science for a long time, they're limited. They can only encode so-called pairwise interactions. And hypergraphs instead can encode group interactions, which are indivisible units with more than 2 elements, and these cannot be represented by graphs. And then many systems are allegedly better modeled with such group interactions and hence hypergraphs. And furthermore, that the kinds of interactions then give rise to new phenomenology, new phenomena, which you cannot obtain with graph-based models or traditional models in network science. And essentially, what I want to claim here is that this is not true, right? These on all counts, these are overstatements or misconceptions about what we're talking about. Instead, what I want to demonstrate here is that graphs do not encode pairwise interactions. In fact, graphs encode barely nothing about interactions. I'm going to show that hypergraph models are actually special cases of graph-based models. This, I think, it's not a very deep thing. I think it'll become clear why it's actually a fairly simple statement. And I'll show that the new phenomenology, which is claimed to be unique to hypergraphs, is actually not unique for hypergraphs at all. It was well reproduced. It's exactly well reproduced with tree-like graphs, which don't have any cliques in them, much less hyperedges. And I will further claim that there's actually very little empirical evidence for the suitability of hypergraphs. And I think it has to do with this conflation, with this kind of confusion about what it is we're talking about. The point is that this literature confuses systematically structure and function. It thinks that a graph or hypergraph defines a system, when in fact it doesn't define a system. It's just the backbone of the system. You still have to say what the system is. And once you do that, you see that a lot of these claims kind of evaporate and things become a lot more clear. Okay, so let's start. So graphs do not encode pairwise interactions. Indeed, graphs do not encode interactions. So let's define what a graph is, right? So a graph is a set of nodes and a set of edges, which are pair of nodes. So indeed, it's defined on pairs. Although, if you would like to, you could talk about an adjacency list, that I'll mention in a second. But that's a pretty standard definition of a graph. And we often use the adjacency matrix to more conveniently talk about the existence of an edge. So the entry of the matrix is 1 if the edge exists, otherwise it's 0, right? So this is the standard definition. Now the point here, and the very fundamental elementary point that I want to get across, is that we're not yet talking about interactions. There's no interactions here. If I give you such a graph, all right? I give you a set of nodes and the agency matrix, and then I ask somebody to please go and, I'm telling you this represents a social system. Okay, please tell me how this system evolves. Right? Tell me how dynamics run on this network. You don't know. I mean, you cannot do anything with this. It's not a functional system. It's just the structure, just the backbone. It tells us something very basic, but very incomplete about the system. Instead, what we need to do, if you want to do something with this, you have to actually define a model, a dynamical model on top of this, a dynamical or a functional model. So very typically what we do is that we assign a variable to a given node, right? For simplicity here, assume this is a scalar, but nothing that I will talk about changes if you put a vector on each node. It's not important, right? And then there are many ways you have to proceed depending what kind of system, what kind of interaction you're interested in modeling, right? So if you have continuous values changing over continuous times, you can use a system of ordinary differential equations where for each node here you put some function on the rest that depends on the rest of this of the system. If you have a probabilistic system, maybe you want to use the Markov chain. If you don't have any dynamics at all, maybe you just want a set of coupled nonlinear coupled equations. Or if you have a general probability distribution, maybe you want to talk about conditional probabilities. It's open-ended, right? There are many, many ways you can have to model interactions. I'm not even trying to be exhaustive here, just to show that, there are many things you can do. What's important here to keep in mind is that the graph does not define these interactions, obviously, right? It only constrains them. It tells us something about them, about something very basic. It just tells us what variables matter, but not much else, right? So what's a network model? How do we connect these two things? Well, the most elementary thing a graph does is to define a neighborhood of a node. So these are the nodes with whom one interacts. Okay, and then, if we have variables, we can then look at the variables that belong to these neighborhoods. So this is this X here. And then the most general thing you can do as soon as you have a graph is to define a function that I'm taking the example here of an ODE system. It of course doesn't have to be that, but just to simplify, just to take an example. So if you're going to write an ODE system, then you're going to say, well, the change of the variable I on node I is going to be some function that takes the variable itself and the values of each neighbor. Now, this is in general a multivariate interaction. Okay, there is nothing pairwise about this. Even though the definition of the graph is based on pairs, what these pairs give you is a set of neighbors. And then you can define any function on this set. And there's no reason why you have to assume that this function somehow decomposes into pairs of interactions. That's not at all, the graph doesn't force you to do that. Expressive graph is not telling you much except what's the support, what are the variables that come into this function. Okay. So this is the situation that we have, right? In the general case, a graph just tells you what are the arguments for each function. In principle, you can have, different function on each node, and the agency just gives you exactly how do what are the arguments, what is the support of such functions. So to emphasize, the graph does not specify how a node interacts, just specifies with whom they interact. So they don't force any kind of pairwise interactions at all. So, of course, you can force it if you'd want to. You can say, well, my function is like this. There's some term on the node, and then there's a sum of pairwise functions. Now you can, weighted by the agency matrix, for example. You'll see this form being used in the literature, as some sort of template for a graph-based models, but that's just not true, right? This definition just contradicts us, but I'll give you some concrete examples in the following, right? So this is definitely a possibility to have this decomposition like that, but that's definitely not a requirement. So I'll just give you some examples of this. It's not something that we are taking out of our pocket or something that should be controversial, I think. You just go and look in the literature. Let's see what people have been doing with networks uh, for, since this field started or before. The earliest example, very concrete example I could find is actually a very famous one. Is the work by Stuart Kaufman, and 60, this is 50, more than 50 years ago, and it's the idea was these random Boolean networks that have been introduced by him, and the idea what he was trying to do at the time was to model gene regulation. So how, what caused the genes to be expressed or not. So he did something very simple. He said the gene can be either on or off. So you have binary variables. Then the system evolves, in a deterministic way like this. So there's a parallel update rule. So the state at a given time is going to be given by the state at the previous time. And to each node, you're going to attribute a function that takes as arguments this set of inputs. Okay, and this function is going to be a Boolean function. So in his model, this function is chosen uniformly at random. So you're going to have this truth table. So these are the combinations of the inputs here, and then the outputs is chosen uniformly at random. Okay, this is what he did at the time. Okay, so again, there's nothing pairwise here. He's not assuming that the interaction somehow decomposes into sums of linear sums or any kind of simplification based on pairs, right? If you want to know what will happen, say if you change an input, you have to look in this truth table. In other words, you have to look at the states of every neighbor, of every input, so you know what will happen to the output. This is a very big topic. I mean, Boolean networks are old and people have been studying this for a long time. There are many different kinds of changes of this. So for example, a different kind of formulation, which is a bit more mechanistic, it tends to it tries to model a little bit better what may be happening in transcription, in gene transcription. These are the so-called nested canalizing functions. So it is that you take the inputs, you order them, you put this is the first, the second, the third, and so on. And then you look, if the first one is taking its canalizing value, which is either 0 and 1, then you know what the output is going to be, so 0 or 1. If that's not true, if it takes the other value, then you go and take a look at the second neighbor. And so on until at the end, you have the default value. Okay, and this is meant to model like how a transcriptor factor binds in the DNA. There might be promoters or inhibitors that are bound there, and this is a very simplified way to model this kind of linear chain of decision, so to speak. So just to give a flavor, right? So, and these are not pairwise interactions. In general, you have to look at, you cannot decide locally, right? Looking at only one neighbor, what the output is going to be. In general, you're going to have to look at the neighbor, the other inputs as well. Okay, so this is a kind of a very early example, and there are many different formulations of this, right? So one of them is the threshold function. So this is, of course, totally standard, right? You take this, you have the weighted sum of the inputs. If they exceed the threshold, then it gives it a value. Otherwise, it gives a different value. Right here is expressed via the Heaviside step function. So this is super well known, right? I don't have to explain this. I think this uses a lot of statistical physics, machine learning. Machine learning people often take this step function and replace it by something smoother, but still you still have the same nonlinearity of the function, right? So again, to say this is pairwise is very misleading, right? Because in general, the output depends on the collection of all inputs. It's very hard here, especially if you have binary weights, that's one thing. But suppose you had weights which are, arbitrarily, right, in the real negative or positive, it's literally impossible to know what is the output is going to be if you don't know the values of the other inputs, right? If you don't only know one of them. And these functions have general expressibility. You can show that if you, with threshold functions, you can encode any Boolean circuit. Of course, with these activation functions, you can, if you chain them as a neural network, you can express almost every function. So these are very super expressive models, and they're not pairwise. It doesn't make sense to say that. So of course, you use that in network science a lot in epidemic modeling. The most basic thing you have is the SI model, it's ordinary percolation, susceptible infected. So we have binary variables, and then you say you have a dynamic. So the simplest case here, the simplest case is the deterministic one, the discrete time. So at each time step, you check if there's an infected neighbor, right? So the function is becomes something like that. If there's at least one infected neighbor, it infects. Now you might say, well, in this case, if the threshold is 1, then you could say you have pairwise interactions, right? Because just if only one neighbor is infected, then you know that the output needs to be infected. That's true. However, it's not symmetric, right? If you consider transition from 0 to 0, then it's not enough. If you want to know if whether or not the node is going to remain, it's not sufficient to look at if you see a neighbor and it has a value of 0, this doesn't tell you that the output is going to be 0. So you still have to, so it's not quite pairwise even in that case, right? But of course, if you increase now the threshold to k to some arbitrary value, this becomes bootstrap percolation, also called k-core percolation. And I'll talk more about this later because it's relevant. And the point is that to talk and belabor the point here, but I want to make this very clear. We cannot classify these models as pairwise. It's not a meaningful thing to do that. So this is the main point about this first argument, that we almost never have pairwise interactions. We can talk about that. In some cases you can, in ODE systems you can do that, but almost never we really have pairwise interactions on the graph model. Okay, now here comes maybe something that may be considered non-intuitive. Hypergraphs, they constrain rather than generalize interactions. Okay, so let's see why that's the case. So what's a hypergraph? A hypergraph is a generalization indeed of a graph where each edge can have more than 2 nodes. So we can represent that with a genicity tensor. So you say that the value is 1 if a given hyperedge of some order exists, otherwise it's 0, right? So C is now an arbitrary set of nodes, okay, with more than 1 element. Okay, so this object indeed generalizes a graph, all right? You can, if a hyperedge has size 2, then you have a graph. And as I'll talk more about this later, if you have 3 or more nodes in each hyperedge, you cannot encode this perfectly with a graph. So it is generalized. It does generalize it. But the point is, how can you use this to define a functional dynamical model, right? That's the thing we have to keep in mind. It's not enough just to stop here at the structure level, at the definition of the combinatorial object. We have to say, okay, how do we use this to model, let's say, a dynamical system? Okay, so what's the difference between a hypergraph and a graph? Well, a hypergraph defines a set of sets of adjacent neighbors, right? So for each hyperedge, there's just a given set of neighbors. So we have then a collection of sets. So so this del I here, this is the particular neighborhood of one hyperedge, and then if you collect them all, we have this set of sets. Now we can think, okay, let's try then to use this set of sets to generalize, right? Let's attempt to generalize the genetic model I described before. So we could say, well, let's take the ODE example. Then we could say, well, the function here on node I is going to be dependent on, in general, the node itself, and plus this set of sets. Okay, but I'm repeating variables here, right? So if I have many sets and they include the same variable twice, I don't have more degrees of freedom, and this is the same variable repeated twice. So this function, however I write it, is going to be a function over the union of the variables included in the set of sets. Okay, so this is nothing other than a function on the projected network, on the projected graph. It's just some particular way of writing this. There's no escape. You cannot escape this. You get nowhere. Essentially, we get that in the most general possible case, I just have a function over all these variables. And so this is the point here, right? So in general, if you have a graph like this and some arbitrary functions on the nodes here that are operating on the neighborhoods, a hypergraph will somehow only tell you that these arguments are grouped in particular ways, and they must be aligned, right? So the groupings that appear here on node 5 must be the same that appear on node 3 or so on. But otherwise, these are just functions of neighborhoods. So to the extent that the hypergraph is telling us anything, it's constraining the set of functions that we can write. Because in general, we don't have to have this alignment at all. Okay, I'll give a more concrete example in a second. This is just the general. Okay, so in other words, because hypergraphs give you more information, they can only constrain the functions that operate on them. A graph, on the other hand, leaves more things open. It doesn't tell you how the functions should be structured. Okay, so if the adjacency is the same, a graph gives more freedom for the model, and a hypergraph gives less freedom. So let's consider some particular cases, and this is, I think, a lot of the confusion that occurs in this literature comes from just focusing on these very contrived cases, right? So indeed, there's this kind of straw man that you see very often, and this kind of model does appear in the literature. It appears, for example, in some very simplified models of in ecology. You see them. I mean, they're useful. They're more simplified. You can, this comes from linearization. So these models are not useless or unknown. Of course, people, you see these pairwise models happening all the time, but they're definitely not the most general model you can have. And of course, we can take this pairwise model, and we can contrast it to a version defined on hypergraph, where instead of having interactions defined on the edges, we have defined them on hyperedges. And indeed, this generalizes this, right? Because if you have pairs here, you get that, and not vice versa. But point number 0, these are just special cases. We cannot reach conclusions from these two cases alone. We cannot reach general conclusions from them. And here's an example of how we can escape these two cases very easily. So suppose now you have a different choice. Now the functions are defined. You take here at each node, you're going to attribute to them a set of functions age. Okay, in this set there are mi. So totally arbitrary. For this node, I want to put it inside 2 functions. This node I want to use 3 functions. This node I want to use 7 functions, and so on. And then you just put the arguments in these functions in whatever way. So y here is just a subset of the neighbors that you want to belong to each function. Okay, so now you see, this is not a hypergraph. This is not defined a hypergraph at all. And by choosing age, I can get both the first model, the pairwise, and I can get this hypergraph as well. It's a trivial generalization of these two cases. Right? Just to illustrate that you can escape this contrived setting very easily. And I want to illustrate 2 instances of this because I think this example is very illustrative. So consider here on the left side. On the left side, you have a model that people like to study a lot in the higher order network literature. You just have these hyperedges, which are highlighted with the shaded areas. And you can see that they correspond to the arguments of these functions here. So for example, node 5, which is over here, it takes 5, 6, and 7. Here, it takes 9 and 10, so 5, 9, and 10, right? And if we go to node, let's say 9, you have the same argument again. So the fact that it gets mirrored like this in these arguments, this is exactly what it means to have this hyperedge. Okay, well, I can take here, just as for illustration, I can take exactly the same functional shape, exactly the same sums. But now I'm going to take the arguments and just choose them randomly. Okay, so I have this model here, and this is the graph that corresponds to it. Okay, and okay, look, I still have the same functions, but now things are wired in a way that you don't still have any hyperedge at all. All right. Now there are two things I want to emphasize here. First, I don't think it's meaningful to say that the model on the left is a higher order model, and the model on the right is not. It's also definitely not true that the model on the right is pairwise. Just look at interactions. All right. So it's important here because I think a lot of time people, when they think about models, they imagine the figures. Like if you forget the equations, if you just look at this figure and this figure, it looks like we're talking about indeed a very different thing. right? It looks like, oh, this is, you have these groups here, you don't have, there are barely any clicks here, right? This is just, there's just one triangle here, there's other one here, but otherwise there are no clicks. But so if you just look at the figures, this looks like something more elaborate, right? But if you just look at the equations, it's the opposite, right? And you have to remember that the equations, this is what defines the system. It's not the graph representation. This is just the backbone, right? And of course, if I take this model here, this graph-based model, and I wire it appropriately, I can recover this, right? Just by choosing the arguments carefully. Okay, and this generalizes. This is what I mean when I say that hypergraph-based models are special cases of graph-based models, because a graph-based model tells you nothing except the adjacency. It tells you these are the neighbors. If you put whatever function you'd like on them. Okay? So now there's another aspect to this that I would like to point out as well. Here in this previous example, I was emphasizing the point that for a function, if you don't want to talk about interaction, and this is what this higher order interaction literature emphasizes on interactions the whole time, then you did have to model interactions, and you cannot talk about graphs or hypergraphs in a vacuum. However, if you do talk about graphs and hypergraphs in a vacuum, there's some things you can say. So for example, there's something which is emphasized in the literature, which is a true fact, that you cannot, in general, recover a hypergraph from a graph. Now we know, and I'll talk a little bit about this later, that you can represent every hypergraph with a bipartite graph. This is true, but then you are augmenting the node set. If you force the node set to be the same, and if you project the hyperedge structure, you cannot recover in general the hyperedge from this projected graph, right? So this is essentially illustrated by this example. So given some adjacency tensor here, lambda, you cannot in general decompose into a projection of a network. This is what this equation says. This is essentially an overdetermined system, right? If you count how many possible entries you have here, this is much larger than whatever set of values you can have for the adjacency matrix. So you cannot have this equation in the general case. And one way to illustrate this graphically is by this figure here, which shows that, well, if you have these three hyperedges here, and if you consider the projected network, which is the black edges, then you cannot distinguish these clicks, right? So you have this kind of nominal clicks, which correspond to hyperedges, but then you have this extra click that appears here, and this is not a true, that's not a hyperedge, it's an induced click, and that's therefore, and just by looking at the network, you cannot distinguish that, you cannot tell. So this is absolutely true, okay? But of course, this doesn't say anything about what I was saying before. You have, this is separate from this. But however, there are many different ways you can specify exactly the same object. That's something I think also is not necessarily recognized in this literature. So even though this is true, the fact that you cannot represent a graph with a hypergraph with a graph like this, with a projection, you can actually represent a hypergraph, any hypergraph, with a multi-layer network, right? So now if you take a graph, if you annotate each edge with a color, now you have only to demand that each click that you're going to consider to be a hyperedge, that is going to map to a hyperedge, must contain edges of the same color. If you do that, then the problem vanishes, right? Then in this case, if we put this set of edges here, then every click that you see here corresponds to a click there, but this click doesn't count because it has a different set of colors, right? And as you can see here, there are many possible divisions. There are many possible decompositions of the edge set that allows you to do that, right? So even completely devoid of any context, right? So you take whatever model you have on a hypergraph, you can always translate into a model on a multi-layer network that makes no mention of a hypergraph. Now, I'm not saying that this is necessarily convenient. It can be more convenient to the hypergraph, but it's just a fact. And also it's important here to mention that the projection runs in the opposite direction. Because there are many multi-layered networks that map to the same hypergraph, the projection runs in the opposite direction. You are actually projecting a multilayer graph on a hypergraph, not the other way around. So they're more general, right? So they're more general representation. So there's not an advocacy for using multilayer networks. It is just another aspect that's important to consider, that even in a completely parametric context where you're forgetting about the interactions, it's not true that hypergraphs are somehow more general than other kinds of networks models have been considering for a long time. So to say that this is higher order and this is not higher order, this is, I think, not grounded on any reality. Okay, so based on this, I'm saying hypergraphs do not offer unique modeling advantages. I'm not saying they're not useful. Maybe they are useful in some cases. I'm certain they're useful in some cases. I mean, we can talk about this later. But their importance is being overblown in the literature, right? So there are 3 points here to keep in mind. The first one I haven't been emphasizing because this is actually recognized, is something I'm going to touch on later. Hypergraphs are just bipartite graphs in disguise because you can separate the node set from the hyperedge set and then just gives you a graph again. And this is not a trivial fact. It means you can use a lot of the techniques and methodologies that we have and theories that have been developing for graphs, also to study hypergraphs, for example, clustering. But I'll leave that aside. I'll talk more about this later. The most important point refers to interactions, right? And so as I have been talking about dynamical functional graph-based models, the generalized hypergraph model, and multilayer graphs, strictly generalized hypergraph parameterization. So hypergraphs may be convenient in some special cases, but they are never necessary. Okay. So let's move now to part 3. So phenomenology means attributed to hypergraph modeling. This, I think, is a problem. So a lot of this has to do with the unsuitability of mean field calculation, and a lot of this has to do with this conflation between notice that I'm separating explicitly the notion of a multibody interaction from a hypergraph, and that's the core of the problem, right? These things are not the same. You can have multibody interactions and not have a hypergraph, right? It's not the same at all. They don't come together. And this is a problem. This conflation causes the problem that I'm about to describe. So this is the model that we have seen before that a lot of people focus on. So you have some, let's say in the ODE case, you have the change of a node is going to be the sum of zero order interactions to or order 1, order 2, order 3, and so on, weighted by a corresponding tensor. And this is a fairly elegant thing to write, right? It's very simple. But then people analyze these systems and they claim that, so they observe some behaviors, for example, they see abrupt transitions, or they see, analyze the stability of a system. And they conclude that they find things different if you're starting changing this. So, for example, if you turn off these three body or four body interaction, if you turn them off and you turn them on, you see different behavior, right? And people conclude, oh, this is important. People have claimed, for example, that such behavior is invisible to graph-based models because they're claiming that the graph-based model can only model this first up to here, right? Which is, as I said, not true. And you can kind of see that just by reading the papers, to be honest, right? Because they prove this to you. They prove it in the following way. So what they often do, it's difficult to analyze this system, right? So you have to make some simplification. So what people do very often is to make a mean field approximation. So they say, well, let's assume that these entries of the hyperedges can be approximated by their ensemble averages. So you have one ensemble average here for the order 2, for the 3, and so on. Okay. Now, once you do that, your system now simplifies a lot because now you have these all-to-all couplings, right? And then you can usually reduce this system into a one-dimensional system, and then you can solve. This is the homogeneous mean field technique. And very often this approximation is asymptotically exact. So for many models that people have studied, this is actually a pretty good approximation. It's an exact approximation in thermodynamic limit, right? Now, there is a big problem with this, though. As soon as you do that, you lost the hypergraph. This is a very elementary fact. The hypergraph doesn't exist anymore. In fact, you can show very easily, I'm pretty much showing this here in this slide, that if you consider now a graph-based model, where instead of having these tensors, you have the same multivariate interaction functions, but then these are not these entries here. They don't give you clicks. They just give you the neighbors, right? So this is an edge between I and J, I and K, and I and L. Okay, so this is a situation where the node I has three neighbors. Okay, and this is when it has two neighbors and so on. So this model is very different from this model. Okay, but if you put here if you do a mean field approximation in this model, then you can recover exactly the same equation. All right. So whatever you see here, whatever you see here, you're going to see it here as well. And furthermore, in this homogeneous case, if you have a sparse network, which is typically what you have, in other words, if the entries will decay with 1 over n, then this network that you're considering here, which has exactly the same mean field as your hypergraph model, it is locally tree-like. So it doesn't have any triangles. So it's a graph. It's like this, right? So what these analyses do, they prove the opposite of what they claim. Okay, so they are proving by showing that the dynamics maps to this mean field that hypergraphs are neither required nor they're relevant for the observed behavior. Okay, so what's happening is that the same figure I showed before. So what happens is that in these works, they are imagining this system here, okay? But the mean field calculation corresponds to this system, where there's no hypergraph anymore, right? And a lot of the claims in the literature, they map to this, and what's even maybe more poignant is that if you actually look at the behavior that you see that they correspond pretty much exactly, at least in terms of the nature of the transitions, to phenomena that have been studied in graph models for a long time. Okay, so for example, I'm showing here bootstrap. I talked about this already, bootstrap percolation. So what happens here if you on a random network, on an add or training network, you have this fold bifurcation that occurs for the order parameter. So there's this saddle point. In this case, it happens twice, right? It happens for here and then there. So there's this coexistence regime. And for the interdependent percolation, which is a slightly different version, you have instead just this fold bifurcation that occurs once. And then you take these models, for example, of high order synchronization, which is pretty much what I have been just describing. So we have a system of differential equations defined as hyperedges. This maps exactly to a tree-like graph, as I have just said. And the phenomenon you see is pretty much the same, right? It's again the same fold bifurcation happening again. You can get this without any hypergraph at all. Simplicial contagion is exactly the same thing. So you have, in that case, that you have some hyperedges, some simplicial complexes, and the contagion needs to happen to all of them. You get exactly the same behavior if you break out completely away these hyperedges. Instead, you have a tree-like graph where you just, again, insist that every neighbor has to be connected, has to be infected, so you're also infected. And you have, again, the same kind of fold bifurcation. It's pretty much the same as you can see here. It's exactly this. There's no new physics at all here, right? You can reproduce it exactly using a tree-like graph, and it essentially recover what, other models have reproduced in the past, right? So these are not new phenomena, and they have nothing to do with hypergraphs. Right. Lack of empirical grounding, this is important as well. So, the literature very often claims that the network that graphs are ubiquitous. Hypergraphs are ubiquitous, ubiquitous and necessary to understand. But we have to keep in mind that neither networks nor hypergraphs are objects of the real world. These are abstractions. Right, you have to be very careful here. You're not going to see, you don't see a graph, you don't see a hypergraph. You use that to model, and you have to choose. You have to choose what's the right abstraction, and for that it's important to take into account the mathematical versatility, right, the interpretability, and the empirical support. Okay, and I would argue that this is not being taken into account when several claims are made. So when people make claims of the general applicability of hypergraphs, they're based on the following arguments, which I don't think are meaningful empirical argumentation. So, for example, often just the existence of toy models is used as evidence, right? Sometimes people talk about theoretical evidence of something, which I don't think is a meaningful concept. Evidence is, it should be, at least in this, I'm talking about empirical evidence here. So this does not constitute empirical evidence. Very often people just reinterpret a bipartite network as a hypergraph. You can do that because these are mathematically equivalent objects, but I don't think this constitutes evidence for hypergraphs. People impute hypergraphs from graph data. I think that's invalid for several reasons. And there is the heuristic inference of hypergraphs in time series, which is an interesting idea, but it's very problematic. So let me go through this in sequence. So toy models are not evidence. Actually, I don't think I have to say this, right? I shouldn't have to say this, but there are many models. The literature is very large. There are many models proposed for synchronization, epidemic spread, opinion dynamics, population dynamics, etc. But the existence of these models by themselves doesn't mean that they represent the real world. Sometimes they compare with empirical data, but this feeds into the next point, which is they don't actually have evidence for what they're using. So one could say that hypergraphs is ubiquitous in the literature. This is absolutely true, but that doesn't mean that they represent real systems. So bipartite graphs, yeah. So this is an example of a recent paper, right, where they were talking about affiliation. So there are people and they're like a co-authorship network. So an author is connected to a paper if they co-author that paper. So we have this bipartite network. Now people have been studying this for a long time. This affiliation network, a plant pollinator network. There are bipartite networks of this kind have been studied for a very, very long time. You can, if you want to, interpret this as a hypergraph. That is fine, but this isn't. You're just using a dictionary, right? You're just changing one thing from the other. If you plot here something like, the higher order interaction size, well, that's just a degree distribution. Okay, the number of so these are things that could have been described just as easily using standard graph-based methodology and terminology and theories. It's hard to see what's the actual what's so different by thinking this in terms of a hypergraph. In any case, this cannot be considered evidence for something fundamentally different. Imputation, this is a real problem, right? So very often people talk about real world hypergraphs. And then look closely, notice that they are putting the hypergraph on top of the data, right? So for example, if you have graph data, then you could consider the maximal clicks as being hyper edges. Or if you have like face-to-face encounters, dynamic face-to-face encounters, which are pairwise, or two people, they're close to each other. If you take a time segment and you see all the encounters that you saw in that time segment, you consider that to be a hyper edge. Okay, now you can do that for just to have something to look at, but this is not evidence for the fact that these hypergraphs are really there, right? Because as this was this first point here says, so this is the imputation relies on the absence of the evidence for hyperedge. Exactly, you're projecting this, you're seeing the hyperedge where it's not, right? So maybe it is there. There's an interesting inference problem here, but this is imputation. And there are 2 points here, right? You can't have it both ways. You cannot at the same time says that hypergraphs are this unique object that you cannot possibly represent with a graph, and then everything you say in the analysis depends on data that came as a graph, right? So either you say that hyperedges cannot be recovered from clicks, or you recover hyperedges from clicks. You cannot have these two things at the same time, right? You cannot say that graphs providing sufficient information to study how data structures, then you will study somehow the structure from graph data, right? These things are completely incompatible. So, this is not, it's not enough. And then finally, there's lots of talk about this. I don't have here the time, but inference of hypergraphs from indirect data, right? So of course, so often we don't have access to the rules of the system. You have to infer from time series, from indirect observations. And this is a very interesting and important topic. It's still something that I would say is an open problem, right? How do we construct networks? How do we construct hypergraphs? It's a very challenging problem. It's very easy to overfit. It's very easy to come, if the worst thing you can do is what I'm showing here on the right, which is to, if you want to reconstruct a network, you just take pairs of time series, you compute a correlation, some sort of correlation between them, and then you put a threshold, and then you change this threshold. You can show very easily that this, there in many important cases, this simply doesn't work, right? You can choose any threshold you'd like, you get nowhere close to the true network, right? Because association and statistical association and correlation are different things, and causation is even something else different. So this is simply just the wrong way to look at it. If we extend this to triadic interactions, that makes it even worse, right? And I mean, not to mention the problem I have been talking about of differentiating structure from order of the interaction, which is very important. There are many papers about this, but I would claim here, we talk about more in detail in the paper, but I would claim that they simply are heuristics that do not even attempt to answer the most relevant questions. For example, the question of model selection, right? So is a reconstruction statistically meaningful? Is it better in a principled way than a graph-based representation? So even though there are claims of ability to reconstruct hypergraphs from data, I would claim this is not yet at the level that it's trustworthy, right? So there are no reliable hypergraph reconstruction methods available, and therefore we shouldn't conclude that these are necessarily meaningful to represent the real world. I would claim that the lack of evidence is not a mere accident. It has to do with what we have been talking about. Right? There's a deeper epistemic issue. There is no interacting system that can represent as a hypergraph, but not as a graph. So if you attempt to identify this, it's not going to work. It's not going to work. You're not going to be successful. So the difference between alternative representations, it has to do with the rules of representation. Right? There's just not adjacencies, but these rules are very often not available in network data. Right? So the rules of interactions are almost always latent. Usually you can only measure structure, right? I'll give some examples of this. So for example, so let's say to consider a protein-protein interaction database. So it tells you that people believe that these two proteins interact. How can you use that to model metabolism? It doesn't tell you very much. So for example, suppose you have a survey of students in a high school saying who are friends with whom. So you have this network. You can even give a weight, you're very good friends, just a little bit, and so on. You can, gives you this big network. Okay, now suppose you want to model how gossip or infection would propagate. The data doesn't tell you this. Does a student need two neighbors for them to be convinced of gossip? This is not in the data. This is not in the answer of the survey, right? Here's a very good example of this, I think. This is the neuronal map of the fruit fly. Is a relatively recent project, and they mapped the connectome, the brain, the neurons of the fruit fly to exhaustion. So you see this beautiful map here with almost every interaction. Well, I misspoke. With almost every edge connection between every neuron, right? It gives an amazing object to study. But now, even if you have this amazing information, or if you want to simulate firing dynamics here, this tells you very little. It doesn't tell you the rule of interaction. It doesn't tell you exactly how a neuron fires when the others are firing. What are the values they can take and so on. This is not included there. Of course, there are a bunch of models for this, but this is not in the data. And if you want to say something about higher order, lower, you have to. This is not going to be obtainable just by looking at the structure, and you have to keep in mind this separation between structure and function have been emphasized. So, just now to recap what we have been saying in this paper. So we're saying that graphs do not encode pairwise interactions. In fact, graphs barely encode interactions, encodes only the support of the interactions. Graph-based models, the generalized hypergraph models, multilinear networks, generalized hypergraph structure. There are no phenomena in hypergraph models that are invisible to graph models, is per definition. And the claim phenomenology that you see, such as abrupt transitions, are not neither new nor attributed to hypergraphs. And the evidence for hypergraph models in the world is very scarce. What we're not saying, okay, I want to emphasize this. We're not saying that hypergraphs are a bad idea or they shouldn't be used. We are free to use whatever representation you find more convenient, right? So I'm sure there are cases where hypergraphs, in fact, there are many cases, right? In physical physics, for example, people use hypergraphs as factor graphs to build beautiful theories and message passing algorithms. In algebraic topology, hypergraphs are super important. So this is not at all bashing of hypergraphs, not in the slightest. Of course, this is useful for all sorts of things. And also, we're not saying that pairwise interactions are sufficient or more important than higher order. That's not the point at all, right? So many-body interaction is something that's has been studied in network science for decades, and this is super important to see. And there are many contexts where they have been neglected, like in ecology, for example. But the point here is that this concept is separable from hypergraphs. So what we are talking about, what we want to happen is that we should take the hype out of the hypergraphs and keep the rest. So with this, I'm finished. The paper is here. There's a blog post that talks about this a little bit more, and Manlio has put frequently asked questions that you can check out in this URL. Thank you very much.
All right. Many thanks, Tiago, for the clear presentation, clear talk. I can imagine that there's many questions, so I was wondering if we could maybe reserve the first 10 minutes for the students from the Beyond the Edge to ask some questions, and then afterwards open it up for the whole group. So maybe please, if you have a question, yeah, feel free to ask.
Maybe I can go first. Am I audible?
Yes, I can hear you.
Yeah, thank you, Tiago, for the talk. It was a nice talk. I just want to ask one curiosity that I have. So in this formalism where we are using graphs to encode all sort of interactions, how do you consider the topology of the network in the dynamics? I mean, when we go with the standard model of intrinsic dynamics plus the topology, you have the graph approach, you have the hypergraph approach. But in this approach, when you have everything as a multivariate function, how do you encode topology? I'm a bit.
What do you mean by topology? This is a word that's used very often. I mean, in network science, people talk about when they talk about topology, they're meaning the structure of the network.
By the structure of the network. I'm talking about the structure of the network.
All right. It's here, right? It's a density matrix, isn't it? So the density matrix defines the neighborhoods. And the neighborhoods define which arguments come. So this is what this figure is showing, right? So which are the arguments of node 1? Well, these are these blue nodes here, right? So they go inside the function. So the structure is telling you what are the variables that matter. In the case of the ODE system, if you take the partial derivative, right, of this function with respect to any other variable that doesn't belong to this set, you're going to get a value of 0.
So I'm just curious. So all the results that we have on let's say the mass stability function, for an example, everything is reproducible even using this approach of multivariate function of ODEs. Okay.
Yeah. I mean, I used these a lot just as a quick example. The notation is very convenient, but of course,
okay.
This is not only ODEs, right? Everything I'm saying is transfers directly to Markov chains, to coupled equations, and anything. It's a very general kind of state.
Yeah. Thank you.
Mm-hmm.
All right. Any other students from our group? I have a question myself, otherwise. In slide 10, I think, you define this. Yeah, this YL is a specific subset of YL of the variables. I'm not really sure. I don't really understand how this is different from defining like hyperedges on a hypergraph.
Because it's different for every node. So if you want to, so this is not hyperedge means that it has to be the same, right? So this is the example here, right? So a hyperedge is like that. So hyperedge, if you look at, let's look at this 1, 2, and 3. So 1, because 1, 2, and 3 belong to the same hyperedge, then these arguments they appear as arguments in the functions of these 3 nodes. Now let's look at this in this case. Here 1 takes 1, 4, and 5, and 2 takes 2, 9, and 13, and here it takes 5 and 6. So you see, they don't line up. So because they don't line up, they don't form a hyperedge. Yeah. So that example, this is the left-hand side. That's exactly one instance of that model I just described in the previous line, right? So this is the y variables are just the arguments. These are the arguments that appear here. And here I'm choosing them completely arbitrarily. I mean, literally I ran this, but I choose it at random. This is how I generated this example. So there's no hyperedge here. Could have happened by chance, but it's very small probability.
Yeah, I understand.
Yeah.
Okay, thanks. Any other questions from the students? Okay, maybe we can move on to just opening it for the whole group. Maybe I would ask to raise your hand and then I will maybe say your name because I can imagine this, yeah, everybody will speak together otherwise. Keith Briggs.
Yeah, thank you. It's Keith here. Yeah, very interesting talk. I'm pretty well convinced by everything I heard. But I'm thinking about one of my interests, mutual information. Suppose I have 3 random variables with some dependency structure, and I'm interested in computing the mutual information, which is a function of the 3 variables. The formula is going to require the joint distribution of the three taken together, as well as the 3 separate joint distribution of pairs. So the question is, even if the dynamics are defined by a system of equations with no hypergraph or hyperedge terms, the mutual information is got a term which doesn't factor into say a product of edge functions. So the dynamics themselves can be defined on a graph without hyperedges, but this property or function which is computed from the variables on the nodes does, to understand it, requires a concept of a hyperedge covering the 3 nodes, linking the 3 nodes. Is there any issue there with fitting that with your picture?
Right. I think so. I think so. First of all, you're right. I mean, these things we're talking about different things, right? So here, indeed, I'm talking about the parametrization of a model, the equations, right? I think one terminology people use are behavior and mechanisms. I've seen this being used. So mechanism are these equations that we're writing here. The behavior are these what comes out of this, right? And this can be measured, as you mentioned, by computing mutual information, correlations between variables, and so on. Now, there are lots of things to talk about. Depends a little bit on the context. I don't think so. If you take in a multivariate Gaussian, which is maybe the simplest example, where this the pairwise entries are the inverse covariance between 2 variables becomes this is the inverse covariance matrix. In that case, we can show that the actual correlation, right? You can do the correlation matrix and inverse covariance is the inverse of the other. There's a very simple mapping between them, but for nonlinear cases, that's not true. For the easy model, for example, it's not true. So indeed, deriving correlations from or mutual informations, or from a given model, that's a non-trivial thing to compute. Whether it requires hypergraphs, I'm not sure. You have to consider high-order structures, right? But I don't think this maps necessarily to a hypergraph. For example, in the dynamical system, these are not symmetric necessarily, right? So I don't know if you would have to include high-order terms, but it doesn't necessarily mean that you need the hypergraph for that. In any case, it's a separate, I think it's a different discussion. I haven't seen a claim that you need hypergraphs for that. I've seen, of course, there's a whole literature about how to represent these high-order terms, right, in mutual information and so on. And again, I want to emphasize here, nothing I've been talking about is really about pairwise versus multibody. I'm putting this issue aside. Of course, these are not the same. I'm not claiming you can decompose always multibody with pairwise. This is not at all the claim. I'm indeed only saying that you don't need to talk about hypergraphs when talking about multibody interaction.
Yeah, thank you. I'm going to need some time to think about that. But yeah, very stimulating ideas. Thank you. Yep.
Thank you.
Mm-hmm.
Any other questions? Well, since I was wondering if I understand correctly, you kind of put the multivariate constraints on the functionality part, so that you don't describe them with hypergraph. But I was wondering why do you actually use a graph then?
Why use a
Why,
graph?
or why would you? Yeah. I mean, you can you use these neighborhoods to as an input for the functions, but why do you not put these constraints also in the functionality?
Well, we're talking about the same thing, right? I think it's not about how, I mean, you can put it a different way. In the case of, I think the OED example is a good one, but it generalizes, right? So essentially, where is the graph? So I've said that you can look, let's see, yeah, so this is what I said right in the beginning. Yeah. Okay, well, how do you, I could just say I have some arbitrary function here and not tell you that I have a graph. That's essentially what you're saying. Well, if I give you the function, we can find out the graph. We just have, in this case, you just have to say, okay, which of the partial derivatives are relevant, right? For some of them are going to be zero. If you have an expression, if you have an analytical expression, you can just see which variables appear, right? But if you have some sort of opaque black box, you can just see which inputs matter, right? Because for node 3 here, it only depends on 14 and 15, which means that if I change 13, directly, there's not going to be an influence, right? The graph is there. The graph is telling which variables matter.
Yeah.
Yeah.
But can you not do the same for the hypergraph if you define some subset of the neighborhoods of node I?
Sure. The point is that it's going to be the same for that, but the point is that it's a special case. That's all I'm saying.
Yeah.
Right? It's a particular way of choosing how this function looks like. So this function f is going to separate, these guys belong to this hyperedge, other guys belong, and then it's going to somehow have a functional shape that distinguishes between them, which is fine. The point is that's a special case.
Yeah.
Yeah. Think of the random Boolean network I gave you the example. They are just choosing a function completely at random. So each node is doing something completely different.
Yeah. Okay. Yeah. Thanks.
Mm-hmm.
Thomas Harley, did you want to ask questions?
Yeah, I wanted to follow up on Keith's question, and forgive me if you may have already touched on this in the reference to Kaufman's work on Boolean networks, but take like a logical exclusive OR gate, right? You can represent the backbone as a graph, two sources and one target. But the only way you could distinguish that from like a NAND gate is if you had the lookup table as well, right? And the lookup table implicitly includes some kind of what we would call like a higher order interaction, right? That's the nature of the XOR gate. And so that seems to me a case where the hypergraph or some higher order interaction like genuinely is necessary, because you need both the backbone, the graphical backbone, and the lookup table that encodes the higher order interaction to distinguish one model, the XOR, from another, an AND gate.
That's literally what I've been saying, that a graph does not tell you the whole information. A graph only gives you the backbone. So let me go to that picture. So if I just look at this figure here on the top, it doesn't tell you anything about how the system evolves, right? None of them do. I have to look at the equations, the truth table, as you said. This defines the system. Absolutely. So a graph, just the adjacency, who is neighbor with whom, tells you almost nothing. It tells you a little bit. It tells you that, okay, I know that if I somehow change these inputs, this might have some effect on the output, but it tells you literally nothing else. But if we to know how the system is defined, you have to know what's the function. In the case of the Boolean networks, you have to know the truth table. That's literally my point. The point is that you need these functions and as soon as you have the general formulation, which is some graph that uses support. Let me go back to the equation. Some graph and some function. That's the more general thing you can say. And this does not subsume the existence of any hypergraph. On the contrary, a hypergraph needs to be a specialization of that, because it needs to say, well, you have these overlapping sets, and these sets are experienced in the same way at each member of the set. That's a very specific thing. In the case of Kaufman's, in fact, it's a directed network in general, where you have for each node there's a different set of inputs, and then in each node there is a different function. Yes, this function is multibody, right? In 1969, so he was looking at multibody interactions then. Nothing new, right? There are many, many examples of these kinds of multibody interaction. You don't decompose in any way into sums of pairwise terms, not at all. In fact, by construction, right, you don't do that. But it has nothing to do with hypergraph at all. There's no hypergraph in a random Boolean network. That's my point.
Okay, I think I'm following. Can I ask as a follow-up? From just a purely parsimony perspective, not a rigor perspective, is this a case where you think a hypergraph might be simply easier? Like you can represent a directed hyperedge from both inputs of the XOR to the target, and that seems just like less cognitive overhead than trying to have the truth table and the backbone.
No, you have to have the truth table. This is just no way. You have to say, if you want to simulate something, if you want to have a model for a dynamics, if you have variables on the nodes, you have to say how this variable changes. You don't have an option there. You have to say something. The graph or hypergraph is not addressing this at all. You need to have a function. So this is one thing. But your question, what's more parsimonious? I think it depends on context. I think there could be a situation where a model like this. So let's put it a different way. It's very simple, actually. This is I'm claiming this is a more constrained model, okay? Because it imposes this extra structure, which is these overlapping clicks, and the fact that essentially this means that these arguments are repeated, okay? So because these three guys belong to the same hyperedge, you see the same arguments appear in each function. So this is the existence of the hyperedge. It is more parsimonious, for sure. If the model happens to be like this, and you don't observe this interaction, and you find out this is going to be a more parsimonious explanation for this than if it came from this model, for sure. Because this model is more open, it's a bigger model, there are more parameters, you can have more freedom here. So yes, if the particular system behaves like this is a more parsimonious explanation. Okay? What I'm saying is that we shouldn't assume this is true, because it's not going to be.
Awesome, thank you.
Yeah.
All right. Questions? Okay, well, if there's no more questions, then I want to thank Tiago very much again for being here. Yeah, the talk is recorded, so I will.
I have a question.
Yeah.
Yes, it was about the previous slide 10. So yeah, especially with this equation 1 here. So if I understood correctly, your like main message is that these, like, when you're specifying a graph model, you're not specifying this subset YL. So this interaction term is something defined on the function, the interaction that is a different concept from the structure, right?
This is true, even though equation 1 is also a particular case.
Yeah. It is
You
a
understand,
particular
yeah.
case, yes.
I have
But my point then, I think, at least from what I see, is that in particular case, there is no structure actually. Like, this is just a mathematical expression, it's just dynamics, and the graph itself doesn't play a role. And why I'm saying is linked to what you said at the beginning, which I agree, is that the graph constrained interaction, it just is it doesn't specify the functional form. But you write this specific type of system, as you said, is a specific type, but here you are constraining also the domain of the function with something that is not encoded in your graph. So for me, this equation 1 here is not a graph model, because the way that you choose the subset, it cannot be defined on pure structure. It has to be defined on dynamics, and thus the domain of the function is defined by the dynamics itself.
Why? Why do you say this is? No, it's a static thing. So it's a set of variables. This is not. This is chosen. It's a.
Yeah, it can be yes, like yes, that is chosen by the dynamics. It's not something enforced
What
by
do you
the.
mean chosen by the dynamics? I don't understand what you say. What do you mean chosen by the dynamics?
I don't know. You're saying that I don't know. Like you're like the system that you're describing is an interaction term between node 1, 2, and 3, for example. Yes, but there is like the graph that you are saying, like, this function is on top, is not telling you that.
No, but look, you're making a mental model. Of course not. So my point is that the graph, this thing here in the first slide, right? This doesn't tell us anything about dynamics.
Yes.
No agreement. So this is.
We agree on this. Yes.
Okay, very good. All I'm saying is that a graph model is one where you have variables in the nodes and there's some function. That's so this so you agree that what I wrote there corresponds to this.
Yes, but I will also argue that a graph model needs to depend on the graph. Like, it should be a function of the graph.
It is, because the neighborhoods here, this delta, I'm showing here in this slide, it is depends on
but then go to slide 10.
But we just agreed that the slide 10 is a case of
I
this.
agree.
So what is there any problem here?
No.
Oh, okay. So what's the difference? Like slide 10.
The difference is that now YL, the subset, is enforced by the function, not by the graph.
No, why are you saying this?
How do you determine
I just wrote a function. Here's an example. There you go. There, look at it. Just this is an instance of that.
No,
what's
but
enforcing what?
So imagine that you change the structure. You cannot change the structure without changing the dynamics as a definition. So
no, I don't think. I'm not saying. I'm writing an equation. I'm not changing it. You're thinking about something else. You're thinking about some property of the function. But look, here's the thing. If you want to claim this is not a graph model, you have to give it a name. This conforms to the definition I just gave you, which is a pretty straightforward one.
This is a dynamical system, yes.
Yeah. So the point is that the graph here is going to tell. Literally, this graph here, I'm writing it here, right? The union of these variables. This tells you which the order which I choose, I think, is completely irrelevant. In fact, I think you're inferring some order, how you choose things which I'm not putting into the definition at all, right? I mean, how I define the model is not a dynamical process. It's just the equation that I'm writing here. So if you agree, as the equation says, that this here, the right-hand side, the special case of the left-hand side, that's all. That's all we need to agree on.
No, I mean, that is not a graph model. That you're not modeling this.
What do you mean?
I mean, if they change the graph, what happens?
I have to change y.
Yeah, so the interaction function itself. So you're not doing like a model, like, I don't know, contagion. No, you are like, there are two things. So one thing is, you know, the whole process. So you know exactly each interaction term. Or do a model, like.
When I write these things, no, I think this doesn't, look, when I write a function, when I say something like this, I have to specify how this function is. So of course I have to choose all sorts of parameters. I could have parameters on the nodes. I can have,
Yes.
I can have colors on the edges. None of this matters. These are just parameterizations. Here I have these subsets that I'm using that particular case to parameterize this function. So that's just a particular parameterization of this function. And why this? Look, you can't. This is a trivial definition. I'm saying that a graph model is one that fulfills this equation. So you cannot at the same time tell me that you agree with what I'm saying here, agree that that's a special case of that, but then disagree with me that this is not a graph model. This is what my definition of this is what this lies. What's a network model? I'm saying this is what a network model is, and this conforms to what people have been modeling for ages, right? It all matches this definition. So if you think that you can have if you can still stratify, talk about different subclasses of network model, it's fine, but that doesn't pertain to my main point.
No, I don't agree on this, but that's okay. Like defining a graph model that doesn't depend on the graph, it seems a
It
bit.
depends on the graph. It's here.
If I change the graph, the dynamics is meaningless. Like you have to change the dynamics. Like it's just that specific system. You're taking a dynamics and you're representing it as a graph. You're not doing the other way around. Like the structure doesn't matter.
No, I don't recognize this. I think you're imposing this order of defining things. I'm not putting them here.
I don't know. It's very strange to me.
No, I think this is a very you can take every single network model ever devised and fits into this frame.
But this is a dynamical system. I think what you're doing is just writing a dynamical system. So it's a system.
I don't disagree. I'm writing a dynamical system, but the point, what does the graph tells us here? The graph tells us which variable matter. In this case of the ODE.
No. That is included into the term YL in slide 10. It's not in the graph. No, the graph is not telling that.
Doesn't matter. Of course, it matters. That's because this function doesn't depend. If we take any set, it doesn't depend here. If I take the derivative, it's going to be 0.
No, but that's, I mean, you know that that's not true.
It is true. Of course, it's true.
But the domain of the function you take, it's based on something that is not defined on the graph. Those YL.
It's literally the graph. It's literally the graph. I'm writing the domain here. This is the domain.
No.
It's the domain.
That is very forced.
It's not forced. It's the most elementary definition you can think of. This is literally, look, it's a one line. How can you tell me it's forced? I'm writing here the degeneracy matrix and taking the set. This defines the domain of the function.
Yes.
It's literally there. We're talking about 3 lines of mathematics.
Yes.
Okay, guys, maybe we can move on to the next question. I see there's somebody else. It's okay for you? Yeah, Benji, don't mess. Apologies for my pronunciation.
Hi. So it's Chris. So I'm just here in the room with Bingy. Thanks, Tiago, for the nice talk. I just wanted to have a quick clarification about your perspective on this equation. That is the last equation on the slide. When you write down your graph-based model, do you fix an interaction function f? So that means that you fix your interaction functions for every fi that that gives the dependency. So that is kind of a fixed differential equation that you somehow model as a graph. Or do you consider, okay, well, given a graph, I now look at the collection of all FIs that are compatible with the graph structure, which is kind of the coupled cell systems perspective, which kind of says, okay, well, you fix your interaction graph, and then you look at any vector field that is compatible with this type of interaction structure. So somehow you have flexibility in the vector field, but you keep the graph fixed. Right? Or is it that you look at a particular dynamical system and then say, okay, well, which kind of graph representation do I have? Because these are somehow, to me, 2 orthogonal questions. So I was just curious what your natural interpretation is when you see an equation of this type, because somehow it doesn't quantify the interaction functions.
Yeah, I mean, I'm not really addressing these questions that you're asking. I mean, I'm only saying that this is the shape that a network model needs to take. Okay, all I'm saying here is that as soon as we have a graph, and in order for this graph to mean something about the interactions, it needs to constrain the interaction terms. It needs to constrain the functions that operate on each node. This is what this slide is saying. Now, how do we choose that? Well, this is, definitely you cannot just read that from a graph. That's literally not included there. The graph just tells you how to select the set. It doesn't tell you anything about the function. So how do you define this? This is depends on which context. I'm not saying that this is random. I'm not saying anything. This depends on each model. If you're going to model some, competition or some population dynamics on species, then you're going to write something that look like a Lotka-Volterra system, which are you're going to have some pairwise terms, for example, because this is how you want to model that. If you want to model Boolean networks, you're going to show write some equations, choose a truth table or an analyzing function. It's totally open-ended. I'm not really delving into how should we choose this.
No, I understood. It makes it clear that, you see the graph as the constraint, but then, you have the extra thing about kind of making a modeling choice. When you have a concrete dynamical system, then you have to say something about what the actual interaction functions are. Just thinking, the reason why I'm asking this question is because this kind of general math literature makes statements for all F that adhere this. So without being specific to a model and for a specific scenario. And I just wanted to get your input on how you see this equation. Thanks a lot.
Yeah, this equation not very helpful. This equation tells us almost nothing, except, very simple. It tells us that there's a network. It tells us how it connects to a network. It tells us, by construction, tells us literally nothing else. And there's very little you can do about this, right? You can say some things, as I just said. You can say, just by knowing what the support of each function, you can tell which variables don't matter. So that, so if you have disconnected sets of variables, we have two components in a network, that no perturbations here is going to affect anything over there. So you can say something for sure. So it gives you the overall connectivity. So, in this case, it's without knowing F, you can say something, right? But it tells you nothing about F, of course not. Yeah, that's my point here. My point is just that, in order for us to say something, we have to say what F is. Otherwise, we'll go nowhere. But just saying this by itself doesn't help us understand anything about F. It's too general.
Thanks.
Right. Are there any other questions?
What's the hand?
I don't see the hands.
Okay.
No questions anymore. Right. Well, then I wanna I close off the seminar. Tiago, many thanks again for your talk, and hopefully see you soon again. And thanks everybody for attending.
Thank you very much. Thank you very much for the nice invitation, and everybody, if you're interested, I'll put again the slides at the ends where you can find some more information. Right, thank you very much.